All right, we're going to look at the intensity of an electromagnetic wave, or the intensity of light, how that varies with distance away from a source. I'm assuming that the source is sending out the electromagnetic waves equally in all directions. That means it's an isotropic source. It does not have a preferred direction. If that is the case, then we just write the intensity of the source is the average energy density in the electromagnetic field times the speed of light c. We can rewrite the average energy density in the electromagnetic wave as permittivity of free space times the average value of the electric field squared. And that is, by definition, for a sinusoidal wave, going to give us epsilon naught RMS value squared. All right. The amplitude of the electric field, or therefore the RMS value of the electric field, falls off as 1 over the distance. We could make the same statement about the amplitude of magnetic field. Therefore, the average energy density falls off as 1 over the distance squared. And therefore, the intensity is proportional to 1 over the distance squared. Now, if we want to ask the question, I have light with some intensity, at what rate is it transferring energy to a unit of area, or some surface area A? So to address that question, we need to take projection effects into account. So there is my unit of area, and there is the direction perpendicular to the surface. So here's my area A. Let me draw in our radiation field. Okay, so the rays of light are incident at some angle to our surface A. We're going to characterize that as the angle between the direction that the light is propagating and the direction perpendicular to the surface. And this is, just think of like trying to cast a shadow with a piece of paper. If the piece of paper is edge on, and it has 0 thickness, then the shadow goes to 0. And if this is oriented such that the surface is perpendicular to the direction the light is propagating, then you're going to have as large a shadow as possible. So it's the same sort of argument. And obviously, if our surface A is oriented such that none of the light is going to hit the surface or pass it through the surface, then there is no energy transferred from the light to that surface. So trying to capture that, the average power, so the rate at which energy is transferred to the surface from our light, is going to be the intensity times the area. The bigger the area, the more energy is transferred. And then we have the projection factor, cosine of theta. And so that's telling us the average power incident on our surface area A. And again, the area A is actually a vector, so its magnitude is how big this area is, but its direction is the direction perpendicular to the surface of the area. And it's that angle between the perpendicular direction and the direction of the incident light, theta, that's going into this projection factor, cosine theta. Another application of this, so this is telling us power, so something about the rate that energy is transmitted. There's also momentum that could be transferred to this area A. And when we talk about the rate that momentum is transferred, what we're talking about is radiation pressure. So I'm just going to give this in two limiting cases. The rate that momentum is transferred depends upon whether this light is reflected off the surface or is absorbed by the surface, or if it's entirely transmitted, then it doesn't transfer any momentum at all. So the radiation pressure in one limiting case is the intensity or the speed of light. So that's just giving us the average energy density in the electromagnetic wave. And that is correct in the limit that all of the light is absorbed by the surface. If instead all the light is reflected, then the radiation pressure is twice as big, because you are not just stopping the light, you're stopping it and reflecting it. So the change in momentum of the light is twice as big, therefore the change in momentum on the area is twice as big. So this could be as big as twice the energy density in the electromagnetic wave, if reflected. And if it's, some fraction absorbed, some fraction reflected, then you're in between these two limits. And transmission through, you're not having an effective momentum transfer from that. So these are the correct values in those ideal limits of if all the light is absorbed, if all the light is reflected.